Hi, grade 11 children. Today we are going to learn about the composition of a mixture, right? So, individual substances that present in a mixture is known as the components. Normally, when preparing mixtures like weedicides, insecticides, they have to be prepared in the correct composition, as well as normally when preparing the solutions in pharmaceuticals. Okay, so the prescribed compositions should be used. So in everyday life, so it is important to understand about the composition of the mixtures, right? So you have to know there are several ways to express the composition of a mixture, right? The composition of a mixture can be expressed as a mass fraction, volume fraction, mole fraction, etc., right? And also mass by volume fraction, even the mole by the volume fraction we will be learning further, right? Let's see as a first thing, composition of a mixture as a mass fraction, right? So example they have given, if a particular mixture is made up of the two components like A and B, we can find the mass fraction of A, that is the component A, by using this formula, right? Mass fraction of A in the mixture is equal to mass of the A divided by the two components, the addition of the mass of the two components, that is mass of A plus mass of the B. And like that, vice versa, if we want to find the mass fraction of B in the mixture, so we can change the formula as mass of the B divided by the total mass of the components, that is mass of the A plus mass of the B, right? So we can define the mass of a fraction of a component like the mass fraction of a given component of a mixture is the ratio of the mass of that component to the total mass of the mixture, right? So let's see the worked examples. See this one, the 100 gram of the solution contains 5 gram of a solute. So if we want to find the mass fraction of that solute, so mass fraction of the solute is equal to mass of the solute divided by the mass of the right solution, right? Mass of the solution. So in your textbook it is printed as mass of the solvent, so please cut that one and change it as mass of the solute divided by the mass of the solution. Okay, because solution is made up of the solute plus solvent. Okay, so mass of the solute is 5 gram divided by the total mass of the solution is the 100 gram, so 5 gram divided by the 100 gram is equal to 1 by 20. That is mass fraction. You also can find it in decimal, 0.05. And let's see the next worked example, right? When 250 gram of a salt, okay, that is NaCl solution, was weighed accurately and all the water in it was evaporated, 10 gram of salt was left. So then they are asking you to find the mass fraction. So very easy, right? A simple question. So mass fraction of salt, all right, is equal to mass of the salt divided by the mass of the solution, right? So mass of the salt is 10 gram divided by the salt solution mass, that is 250 gram, so 1 over 25, simply 0.04. Right, now the composition of a mixture as a volume fraction, as I said you earlier, right? So as we define the volume mass fraction, so we also can define the volume fraction. The volume fraction of a given component of a mixture is the ratio of the volume of that component to the total volume of the mixture, right? Example, in a mixture, if a particular mixture is made up of two components A and B, then if we ask to find the volume fraction of A, then volume fraction of A is equal to volume of A divided by the total volume of mixture of A and B, right? So vice versa, if the volume fraction of B is asked you to find, and volume fraction of B is equal to volume fraction of B divided by the total volume of the mixture of A and B, right? So let's see the worked examples. So see this one. A solution of final volume of 250 centimeter cube was made by adding distilled water to the 25 centimeter cube of ethyl alcohol, right? So what is the volume fraction of the ethyl alcohol in this solution? So volume fraction of the ethyl alcohol is equal to volume of the ethyl alcohol divided by the total volume of the solution, that is 25 centimeter cube divided by the 250 centimeter cube. So 1 by 10. So simply 0.1 you can give in decimal. Next question. How do we prepare the 500 centimeter cube of an aqueous solution of acetic acid composition of 1 over 25? V over V composition they have given. Here they have given the V over V composition. Now we want to find the volume of the acetic acid. So follow the same formula, right? So volume fraction of the acetic acid is equal to volume of acetic acid divided by the final volume of solution. So here subject, okay, what do we know? The total volume. So that is 500 centimeter cubes of solution, and we know the volume fraction of the acetic acid, that is 1 over 25, and subject the substitute the values given, and we can finally find the value of volume of acetic acid, right? So that is 20 centimeter cube, right? 20 centimeter cube. You also can call 20 milliliter, right? Then right, so here what do you understand is the acetic acid solution with the composition of 1 over 25 is obtained by measuring 20 centimeter cube of acetic acid, that is accurately, and adding water to make the final volume up to the 500 centimeter cube of solution, right? So in further classes we'll be learning how to prepare the standard solution and all, right? You will get the clear idea of it, right? So like mass fraction, volume fraction, now it is the composition of a mixture can be found by the mole fraction also, right? So when we are trying to define the mole fraction of a component of a mixture, that is the ratio of the amount of moles of that component to the total amount of moles of all the components in the mixture, right? So if a particular mixture is made up of the A and B components, mole fraction of A is equal to the number of moles of A divided by the total number of moles of that mixture, or we can say amount of moles of A plus amount of moles of B. And if we want to find the mole fraction of B, the amount of moles of B divided by the amount of moles of A plus amount of moles of B, or that is the total number of moles, right? So let's consider the worked examples. If we consider the first worked example, that is what is the mole fraction of the sodium hydroxide in a solution made by dissolving 40 gram of sodium hydroxide in 180 gram of water. So here the question is to find the mole fraction, but the question is with the only mass. So what is our duty? First of all, we have to find the number of moles. For that, okay, we need the mole mass of the water as well as the sodium hydroxide. So let's consider one by one. So in your questions, relative atomic mass of each atoms will be given, right? Each element will be given, so don't worry. So, and also you have to know up to 20 elements, you have to know the values, okay? And so for the molar mass of the water, right, okay, molar mass of the water, that is H2O. So 2 hydrogen into 1 plus oxygen 1 atom, so 16, so that is 18 gram per mole. So when we write the molar mass only, we put the unit gram per mole, right? For relative molecular mass we don't put, right? So you know what, the number of moles, the formula number of moles is equal to the given mass divided by the molar mass, that is the formula. So that's what the amount of moles of water in the solution is equal to given mass is what, 180 gram divided by the molar mass 18, so the value is 10 moles, then again the molar mass of sodium hydroxide, NaOH, right, Na23, right, relative atomic mass of sodium, plus oxygen 16, plus hydrogen 1, so totally 40 gram per mole, right. So number of moles of sodium hydroxide in the solution is given mass divided by the molar mass. So given mass is 40 gram and molar mass is again the 40, the 1 mole, right. So now we have found the moles, so now our work is going to be easy. So the question is mole fraction of the sodium hydroxide in the solution. So you know the formula. So mole fraction of sodium hydroxide in the solution is equal to number of or amount of moles of sodium hydroxide divided by the number of moles of water plus number of moles of sodium hydroxide. So amount of moles of sodium hydroxide is 1 divided by below amount of moles of water is 10 plus amount of moles of sodium hydroxide is 1, so 1 over 11. Okay, so 1 over 11 is the molar fraction, right. Then mole fraction of the water is what? The amount of moles of water divided by the amount of moles of water plus amount of moles of sodium hydroxide. So 10 divided by 10 plus 1, 10 by 11. So just see this one. If we consider the sum of the moles of fraction is equal to mole of the fraction of water plus mole fraction of the sodium hydroxide. Why? Because there are only two components in that sodium hydroxide solution. So we add the fraction of the mole fraction of the both components. So when we add, it comes as 1. So not only for the sum of the mole fraction but also the sum of the mass fraction as well as the sum of the volume fraction is equal to 1, right. And also another thing you have to know, there are no units, right. There are no units for the mass fraction or volume fraction or the mole fraction of a mixture, right. These are the two things, easy things you have to consider, right. And also you have to understand, normally when expressing the composition of a mixture as a fraction, okay, it also can be expressed as a percentage as well as parts per million, ppm. So when you are getting A levels in when you are learning A level chemistry, you will be learning about the parts per million in detail. Now you just want to have an idea only, right, how to find. Okay, composition as a percentage means to find that one, just multiply by 100 to find the composition as a percentage. To find as a ppm, okay, so parts per million, so you have to multiply the fraction by into, right, 1 million, right. Okay, so these are the two ways that you can further express. Alright, so just see the worked example. 20 gram of magnesium oxide, right, contains 12 gram of magnesium. Calculate the fraction of the magnesium, mass fraction of the magnesium, and express it as a mass percentage. So mass fraction, you know how to find, mass of the magnesium divided by the mass of the magnesium oxide. So 12 gram divided by the 20 gram, that is 0.6 mass fraction. Okay, then if we want to express as a percentage, multiply by 100, so that is 60 percentage. So the mass percentage of the magnesium in the magnesium oxide is 60 percentage. Still we can express the composition of a mixture in terms of the mass by volume composition, right. So let's see the worked example. So normally if we are trying to define this one, mass or volume composition, so it is known as the mass of a solute contained in a unit volume of a mixture, right. Mass of solute contained in a unit volume of a mixture, right. So here 1 decimeter cube, so actually you have to know, children, 1 decimeter cube is equal to 1 liter, right. 1 decimeter cube of G1 solution contain 5 gram of sodium chloride. So if we want to find the composition of the sodium chloride in terms, so mass or volume composition of a solute is equal to mass of sodium chloride divided by the volume of the solution. that is 5 gram divided by the 1 decimeter cube, that is 5 gram per decimeter cube. You the here so far we saw what is that mass fraction, volume fraction, okay, and also the mole fraction. All three composition of a mixture that is expressed as fraction have no volume, have no units. See this one here, this one has unit. This composition of mixture expressing way has the unit, so please don't forget to put the unit. So gram per decimeter cube, right? And the next way is expressing the composition of a mixture in terms of amount of, okay, moles divided by the volume, that is N by V. So you know children, right? So normally mole, okay, mole is the SI unit or the international unit to express the amount of matter, right? So here the composition given in terms of the amount of moles of solute contained in a unit volume of a solution. So it is also known as, or it is this composition expressed in this way is also known as the concentration, right? Concentration. All right, another term for the expressing the mixture of composition by N by volume is also known as what? Expressing the composition of a mixture in terms of concentration, right? So let's see the worked examples. So 2 decimeter cube of a solution, right, contains 4 moles of sodium hydroxide, right? Find the sodium hydroxide concentration of the solution. So here we have the we know the formula, number of moles divided by the volume of the solution. So we can substitute it. So right, so amount of moles of the sodium hydroxide is what? 2 in the 2 decimeter cube of solution is 4 mole. So you can divide 4 mole, okay, 4 mole divided by the 2 decimeter cube, that gives the 2 moles, okay. So actually it means what? The number of moles, right? The number of moles or amount of moles of the solute contained in a unit volume is shown by this worked example, right? So if you want to say the concentration of the, so in another term, concentration of the sodium hydroxide in the solution means what? How many moles, or the amount of moles of a solute that is present in a unit volume of a solution. That means in the question they have given in the 2 decimeter cube of solution the 4 moles of sodium hydroxide is present. So the concentration means what? In 1 decimeter cube of solution how many moles are present, that is the question. So you also can find in this way, right? If 2 decimeter cube contain 4 mole, then how many moles present in 1 decimeter cube? Okay, so that is 2 mole. So directly you can express 2 mole per decimeter cube, right? The don't forget the, okay, forget to express the what? Answer with the unit. Next question, what is the mass of the glucose required to prepare 1 decimeter cube of a 1 mole decimeter cube of solution, right? So you may think it is little bit complex, but it is not. It is very easy, you can easily find. So you just see one by one. So normally they are asking the mass, okay, mass of the glucose needed to prepare the 1 decimeter cube of a 1 mole decimeter cube solution. So directly just think, so they're asking, so if we know the number of moles that is present in the 1 decimeter cube, we can easily solve the problem. So and also they have given another clue. They have said in 1 mole of 1 mole decimeter cube glucose solution, that is the concentration. So understand children, so in 1 decimeter cube 1 mole is present, right? In 1 decimeter cube 1 mole is present. So if 1 decimeter cube contains 1 mole means so you already know the molar mass, how to find the molar mass of the glucose. So C6H12O6, 6 means what? 12 into 6 plus hydrogen 1 into 12 plus oxygen 6, so 6 into 16, so 180 gram per mole. So molar mass means what? In 1 mole 180 gram is present. So if 1 mole contains 180 gram, so the question is what is the mass of the glucose required to prepare 1 decimeter cube for 1 mole decimeter cube. So if 1 decimeter cube contain 1 mole, you already know the molar mass is also equal to 180 gram per mole. So then the mass of the glucose required is equal to 180 gram. Okay, and also otherwise even you can use this formula. Number of moles is equal to given mass divided by the molar mass. So number of mole is 1 mole, okay, is equal to the question is the given mass divided by the molar mass. So 1 into 180 is equal to 180 gram. So see the second question. Worked out the mass of glucose that should be weighed to prepare 500 centimeter cube of solution of 1 mole decimeter cube glucose solution. So now we have to find the mass of the glucose that is required to prepare the 500 centimeter cube of solution. So here in above question we have found that in 1 decimeter cube, that is 1000 centimeter cube, okay, that is 1000 milliliter, that is 1 liter. What is the mass required to prepare? 180 gram. So now the question is and also the same concentration they have asked, what is the mass of the glucose that is needed to prepare in 500 centimeter cube of a 1 mole per decimeter cube glucose solution. So if we know in 1 decimeter cube that is 180 gram, then what is the mass of the 500 centimeter cube of solution? So find, okay, divide by 2, that is 90 gram. Okay, so these are the methods of expressing the ways of composition of mixture, children. Okay.